Okay, it's after 11, so hello everyone. I plan to conduct this session in English, but if you are all fluent in Polish, I can switch to Polish. So does anyone prefer English actually? Okay, so let's conduct it in English. So thanks again for coming here. My name is Mariusz Strzelecki, and the title of the presentation, you can see it on the screen, What Apache Kafka is Not. The inspiration for the title was actually this TV show, Vabank. Do you recall this show, the rules? Okay, some of you know. This show was popular in Poland in late 90s. The main rule of this show was that the contestant was given an answer, and its task was to prepare a question that matches the answer. Okay, so this was like a flip. So yeah, you can imagine that this show, if this show would be played nowadays, you can imagine a category message buses, and the participant says, okay, I would like to take a question for 500 zlotys. Okay, the answer is this message bus is used in Spot, in Uber, Spotify, Netflix, and Airbnb. And the proper answer in form of the question would be, what is Apache Kafka? But you can spot this note on the first slide. I will reveal the details later. Now a few words about me. I work as a data engineer at Fandom. This company is not very popular in Poland, but we host a popular site in US, actually the third most popular site in US. I spent last 4 years working with Hadoop, Spark, and Kafka stack in distributed world as an architect, as an operations guy, as a developer, as an analyst. So I know this world from different sides. No, I know this ups and downs of this world. Before we go to the main topic, let's assure we have a common ground on publish-subscribe paradigm. So let's start with a story. Let's say that you are a startup, you just developed some front-end application, and there is some logic there, and you notice that this application produces some metrics, some data. They can be like a number of invalid login attempts, or the mean request time, or number of invalid or internal server errors, and you decide to store these metrics. Natural way to go is to deploy an additional service like metric server and just push the data there. And this is perfectly fine. But then you realize that actually every service produces metrics. The databases produce metrics, the other services, even the metric server produces metrics. For example, how many metrics was provided. And you end up with something like spaghetti. So this is not very different than the traditional monolith when everybody communicates with everybody. Yeah, there are multiple producers, but you can imagine there can be also multiple consumers, like you can store these metrics for troubleshooting, but maybe you want to design some dashboards to show them in real time, or maybe you want to do some anomaly detection, so there can be multiple consumers and multiple producers of the same thing. And this is the world, this is the place where publish, subscribe plays a nice intermediate role. Because instead of pushing the data to the servers directly, you push them to something that is called publish, subscribe broker. Okay, so every message, every event, instead of just being put to the end server, this is put to some publish, subscribe system. And there can be multiple producers of the same types of events. Okay, so this is like we make our microservices world loosely coupled. The producers do not know about consumers, and consumers do not know about producers. They are only interested in exchanging data. But you may think, okay, the metrics, yeah, one technical example, but if your application produces logs, maybe you can use the publish-subscribe paradigm too, for example, to push the data to some log search components or to security analysis components. If you are tracking your users, you may be interested in getting these events to some offline store for further analysis. But still, they are like technical publish-subscribe systems. But there are way more applications of this technique. The most popular one is asynchronous event-driven microservices communication. If you develop the software nowadays, you probably use microservices. They can communicate synchronously or asynchronously, or they can communicate using events. And there are communicating using events is actually playing the more and more important role in our system because of its capabilities to be resilient to issues, to replicate to second data center, and so on. But this doesn't only apply to microservices. If you play multiplayer games, then usually your moves are being produced as events to some server, and other members of this game, other people in the same game room, are consumers of your events to reflect your state. So actually, yeah, the event-driven programming in multiplayer games plays a significant role. Also, it is said that there are two hard things in IT: the naming conventions and the cache invalidation. And publish-subscribe can help here, because when something is changed, you can fire an event, a notification, something is changed. Everybody who cached this entity previously can just remove it from cache. So it maybe it simplifies the way, but this is not only for cache invalidation. You can imagine you are developing a stock market application, and instead of asking the stock market every 100 milliseconds, what is the price, what is the volume of some company, you can just listen for events. You can tell stock market, please fire an event when something is changed, and I will just keep listening. It's much more performant in this scenario. Also, task queue, you can, like sending an email, you usually shouldn't do this from the request to make a request as simple as possible. So you can fire an event, and this will be consumed by some event background job that will fire an emails actually. But the actually very nice and new application of publish-subscribe is Internet of Things. You know this trend. This trend that there will be a lot of sensors, a lot of devices that will communicate. I even found the research that till 2020. 26 billion devices will be communicating via internet or other networks across the globe. So I can imagine talking directly from the sensor to some server that is interested in this data. In this field, the event-driven systems, the message brokers will play a significant role. And well, since this is as popular as I just shown you, let's play a role of software architects. And let's develop a message broker, event-driven system from scratch, having nothing. Let's assume that we want to handle these IoT services. We don't want to use any tools that are on the market because we are architects. We want to create something from scratch. And our message bus needs to provide these key features, these 4 key features. First, it needs to be distributed. This will be used in a distributed system like this IoT, and we don't want to rely on any one machine. If the broker is down, we want the system to be functional still. We want this to be fast. We don't want the system to be bottleneck. For example, if a sensor is sending some data, we want the response to be quick. Also, we want reliability and durability. If the consumer is not listening for the data in this moment, for example, it's being restarted, we don't want the data to disappear, so we need to store them somewhere. And the API should be easy too. The sensors, the devices in IoT are usually low-powered computers with a small amount of memory, counted in megabytes. The API shouldn't be should be as easy as possible. So, this graph shows what we are trying to develop. We have some producers of some data, we have some block, and we want to implement consumer that first subscribes to the events of given type and then retrieves the data. Okay, this is actually what we are going to develop this block in the middle. So how would you do this in the simplest possible way in 12 lines of code, like a POC, you know? Okay, I have an idea. Let's put responsibility to something else. Let's integrate a database. We have plenty of databases we can add here, and let's write something like this. We have a controller on post. We will just add an event to database, okay, to a table. It doesn't matter if this is SQL or NoSQL. Actually, yeah, it doesn't matter at all. And if consumer asks us, okay, are there any events to process? We will look for one, maybe in blocking way. Then we will delete it. We don't want this to be provided as a duplicate, and we will return it. Okay, so in easy steps, we have something like stateless, because this service is completely stateless, service that has a nice API. But there is a big disadvantage of this. This is not effective. This is never going to be effective. Because the databases are created to support CRUD. So create, read, update, and delete. Actually, we don't even update the events. We just append them, and we retrieve them. So why to use something that was not designed to? And so let's find a similar analogy. When you run a server, any application you can imagine, it produces logs, like messages. And usually you redirect these logs to some file on the file system, okay? So you start the application, the logs are being redirected, and if you are interested in what the service is doing, you just type tail -f, path to the log file, and you're reading these messages. If you want to stop, you just hit Control-C, and you are no longer a consumer of this event. You can restart the application, and the logs will be durable. So let's use this analogy, like producing the logs from any application, to implement our message broker. So we can imagine something like this on the slide, where producer comes to us, we'll just append an event at the end of the file, like a bytes in the end of the file. And when consumer asks us, are there events, please give me an event with offset 8, the 8th or 9th actually event in the queue, we will just retrieve this from the file. The implementation is even easier, because on post we will just append to a file, and on get we will just define the position, starting and ending position, above from the file, what should be read and deserialized. We will deserialize and return it to the consumer. So yeah, we lost durability because now we are relying on this one server. If the server is down, it's not the good situation for us. But we have nice capabilities. We can integrate multiple consumers, because when consumer asks for an offset, we are calculating the offset separately, and we are returning the data. What is more, we can have multiple producers to our data. Let's say our data, our topic. So let's make a definition that topic is a set of events of the same type. So we can have two producers to one topic, because we have an abstraction over this file, so we can synchronize the appends. So yeah, more or less it will work pretty nice. What is more, we can have multiple topics. We can have, for example, the producer 1 can gather the temperature readings, and the producer 2 will be the humidity sensor. And let's say that consumer 1 is interested in every environment sensor reading, and consumer 2 is interested only in humidity. So with this simple implementation, we can cover this scenario too, quite easily. But I wouldn't recommend you to use this kind of code on production due to a small issue. What about high availability? We have HA on producer's side, because if producer is down, it will not provide any data, but we can have multiple producers of the same types, so this is okay. But what about brokers? If a broker is down, well, we can't produce any kind of message. We can't read them from the consumers, and if broker vanishes, we lose access to the data. So this is not durable at all. Also, for consumer, we have one consumer that consumes data. If the consumer is down, for example, this is a split in the network, we can't do anything. We can't access the data because maybe the broker is down, maybe not, but we can't reconsume the data in another way. So let's do some simple trick to make it highly available for brokers first. Usually when you have one instance of a service and you want to make it HA, you just deploy a second service with the same code, with the same logic. So let's deploy 2 brokers on different machines, in different availability zones, or on different racks in the data center. And let's tell producer to put half of the events to one broker and the second half to the second broker. Okay, let's call this parts of the topic partitions or shards. Let's stick to the name partitions. So you have one partition and the second partition. The API for consumer will be, this will be a bit harder to implement because maybe we need 2 processes, maybe 2 threads to download this data, but still the consumer can connect to both brokers and retrieve all the data that we store there. If we have 2 brokers, and if we split any topic into 2 partitions, this will be not hard to maintain. Sorry. But what if we have 10 brokers? We may need some cluster coordination system because we want producer to know what topic, what partitions are on what brokers, the same for consumer. So maybe we need some coordinator to exchange metadata. I vote to integrate Zookeeper here. Do you know what Zookeeper is? Okay. Half of you know. So let me introduce this. This is the simple configuration management system with the service discovery capabilities. This is resilient to network partitions. This can be consistent if this is used in a synchronized way, and you can achieve availability if you are not interested in consistency. So yeah, pretty nice service to hold our configuration. So yeah, we have a coordinator. Producer can connect to the keeper and ask, okay, who holds the partitions for the topic I'm interested in writing to? The zookeeper will respond some information, and yeah, producer knows what to do. But there is still one gap. One gap is that if the broker on the left is down, we don't have access to the data. So producer can then produce the data to the broker on the right, and consumer will consume them. But what if consumer wasn't able to capture all the events produced on the broker that is down? Well, if we can start this broker again, then consumer maybe will read these events. But if this broker is vanished, for example, it was on Kubernetes, yeah, you may lose data. We don't want to lose data, but we have already on our picture a protocol that helps us in this situation. This is consumer protocol. So we can say broker on the left, be the consumer for all events produced to broker on the right, and vice versa. So we doubled space usage, but we are durable to the issues with the brokers. If you kill one broker, the second broker holds all the information. So we will not lose the data in this scenario. So yeah, we are resilient to killing brokers, even to removing brokers' data. So I think that we have HA on brokers. What about consumers? Well, we may use the same trick as we did for brokers. So you recall we deployed 2 brokers with completely the same code base. So let's start 2 consumers that do the same business logic. Consumer 1.1 and consumer 1.2, okay? Let's call it a consumer group because this is a group of consumers, so we need some ID for this consumer group. So let's say that these are the temperature consumers. and by this ID, the cluster will know to provide half of the data to one consumer, like one partition to one consumer, and the second to the second consumer. So unique, distinct set of data. Yeah, so far so good. But what if consumer dies? Well, we want the second consumer to take said partition, but there is a problem. We don't know on what index this consumer finished processing. Let's say the consumer was on event 6, okay, and it dies, and consumer 1.2 tries to read this partition, but it can't start in the beginning because we would get duplicate processing. So we need some storage. We need some database, and for example, after processing of each event, we will dump the data to the storage. This event won't process. We want this to be reprocessed again. But this adds complexity in our system, right? Because this is the database to maintain and so on. So we could use Zookeeper. We have already Zookeeper in our system, but Zookeeper, yeah, we use Zookeeper for the cluster coordination. So we probably don't want to expose this API to the consumers because we have multiple consumers. But we already have a kind of database on our picture because the brokers are actually a database. So you can imagine that after processing event 6, the consumer can produce event. I processed event with ID 6 at offset 6. I don't want this to be reprocessed again. And if you replicate this offsets topic, actually offsets data, we can be sure that whole cluster knows at which offset each consumer finished reading. Okay, so we can lose any consumer. Every consumer has state of whole consumer group. The cluster knows the consumer group. So I think that we achieved HA in consumers too. Just to recap, we can have multiple producers to the same topic with ease. We can have multiple brokers. We can kill brokers. We can have multiple consumers, and we can kill them as well. So we have something like the system that can be deployed in production. And you see, we developed this from scratch since 10 minutes. So there are some challenges to this. One is that disk space is not infinite. So if we are keeping appending to a file, you feel that finally we'll run out of space. But there is a solution that you already know. And I will use this analogy to server logs. When you produce a server logs, you usually roll the data. For example, if the log file is 10 megabytes in size, you rename it the file, you create a new one, you can compress the old one, and you, for example, agree to keep only 10 megabytes files. So you know that your logs won't exceed 100 megabytes. Let's implement the same scenario here. So when producer produces events to our system, and the file is bigger than, let's say, 1 gigabyte, let's close this file and let's start appending to another file. And let's call this file segment. Okay, this is a segment of files. And when we are running out of space, or after some time, or if you are sure that all consumers consumed all the events, we can just remove all the old files. So we will not run out of the disk space in this scenario. But there is other issue. Here comes consumer and says, okay, I would like to start reading at offset and then some large number. And looking in all files to find that message that he's interested in, and the next message is maybe time consuming, and we want to be fast. So let's implement something that we already know from databases, indices or indexes. So for each segment, let's introduce something like a metadatabase specifying at what file of the segment byte the message starts. Okay, so if the consumer asks for some message, let's find quickly which segment contains the data. Then let's look into this index file. Let's do a binary search over this file, and we know the position in the file. We are seeking to this position. We are reading the data. pretty straightforward way. And yeah, we have a fast access for consumers, even if they are asking for some really really large offsets. I don't know if you would design a message broker in this way, but if you did, you would design a Kafka. This is no more than a Kafka. Even if you know Kafka, you probably know that even the naming matches. So you have partitions, topics, we have segments. Kafka, the software written in 2011 in LinkedIn, written in Scala and in Java. In 2011, guys in LinkedIn moved to microservices system, and they already had a problem with throughput. So they had too many messages, and they didn't find a single solution on the market that would handle that traffic. So they created a completely new one from scratch. A story about the name itself is interesting. I have a note from Jay Krebs. This was one of the designers. He said, I thought that since Kafka was a system optimized for writing, using a writer's name would make sense. I had taken note of classes in literature in college and liked Franz Kafka. Plus the name sounded cool for open source project, which I completely agree. This is well-established name. Actually, Kafka is currently, I found a statistic in the internet, so I'm not sure about it, but that 30% of Fortune top 100 companies, so the most successful, the most rich companies in the world, use Apache Kafka in some way. So you may feel like, Apache Kafka became a standard in high throughput message processing. Then why? Why Kafka was so successful? Due to some things that I noted here. First, it doesn't cache data. You may feel like, well, when we are developing a software that accepts some kinds of events, we may want to store the data for some time because maybe consumers are processing the latest data and they will be interested. Maybe let's introduce some concurrent hash map. Let's put the data here because somebody may be interested in this. Instead, Kafka caches nothing, but it relies on operating system. If you know from studies, for example, how the operating systems work, when you want to read the data from the disk, they are actually mapped as pages in memory, and you read the data from memory. So again, the operating system usually gets more than the data we want to read because it thinks, okay, if you're interested in this part, maybe you will be interested in next parts. So Kafka uses exactly this paradigm. If the producer writes the data, they are written to disk, but they still exist in this disk page cache. And when the consumer comes from the data, and if this disk page is available in memory, let's say that the data were previously written a second ago, the consumer don't hit the disk at all because they are in memory. There is, of course, some background process handled by operating system that writes the data into disk to make them persistent, uses journaling and so on. But in this condition that you have producer and consumers reading newest data, you don't hit a disk at all. I mean, this doesn't influence the performance, okay? Even, what is more interesting, Kafka uses zero copy. So it stores the data exactly as the consumer will need them. So when consumer comes from the data doesn't even flow through the application. They flow directly from this page cache to the network socket. Okay, so you don't even process the data. This is the reason for. This is why the high throughput is actually nicely possible here. It doesn't maintain cluster configuration. It relies on Zookeeper because what is the point to implement something that already exists in the system? So, for example, if you want to create a new topic to get the data, metadata from the topic, you can connect to Zookeeper and get all the data from there. Also, all brokers watched for the changes in Zookeeper. So if you change something in Zookeeper, all brokers get notified. You don't need to coordinate this. It compacts data. This is interesting. If you want to store a snapshot of database in Kafka, And you know that the segments will be finally removed when this log compaction, when this log deletion works. Well, you may lose the entities that were not updated in, let's say, last week. But instead, you can use compaction. When you write the data to Kafka, you place a key and a value, and the compaction is a method to remove the data, but to leave the newest value for given key. So if you put all the data you have in database to the topic and you set the compaction, you can't lose the data. They will be still there. This works well when you do some stream processing because you don't need to access external database. You can build in-memory database snapshot. It's easy to monitor and maintain. It exposes a lot of metrics through JMX, and it is backward compatible in the previous protocol versions, but in the way that the brokers implement a lot of APIs. So if, for example, you want to upgrade the Kafka, you do a rolling upgrade, they all communicate using the old protocol, then you switch to new protocol, and this is without any interruption, works well in the scenario. So you can upgrade the Kafka. Actually, you don't need to do any downtime, any maintenance on Kafka side. It just works. When talking about Kafka, and in general about publish subscribe mechanism, it's important to cover something that is called message delivery guarantees. And the tweet for Matthias Veres, very famous actually, and actually this is sketchy, this is the idea. There are two only hard problems in distributed systems, especially in this messaging. The second is exactly once delivery, the first is guaranteed order of messages, and the second is exactly once delivery, right? This 140 characters, and he did it just brilliantly. So let's focus on this ordering. Kafka maintains ordering within partition. What does it mean? In every second, in every time, only one broker accepts writes for a partition. So if you have ordering in one process, this is much simpler than guaranteeing ordering in whole cluster because the nodes don't need to agree on the ordering. So this works well, but only in one partition. But this partition can be replicated, and this is replicated exactly in the way that it was written. So actually, after this replication, all followers or replicas have the same ordering. So we have strong guarantee or ordering of the messages. Ordering, when they come, they are written in the same way, in the same order, but only within one partition. But there are more. At least once. This guarantee that we may expect from messaging system stands for we want every message to be produced, and we are all duplicates. You know, in distributed systems, when there are network issues, when there are restarts, this is hard to achieve a full consistency. So yeah, this is some simplification. If everything works well, we get one processing of each message. But if there are troubles, we can assure at least once. How Kafka does it? When the message 1 is produced, broker replies acknowledged. When the message 2 is produced and broker doesn't provide this acknowledgement back, then producer can retry and broker will acknowledge. And depending on the state of the broker, the message is duplicated or not. We don't know. Because if the firing message of message 2 was lost, then there will be no duplicates. If acknowledgement was lost, there will be duplicates. So yeah, we have a guarantee like this. On the consumer side, when you are consuming data, if you first process the data and then you move offsets, then if you've processed some batch and you wasn't able to move offset, for example, the consumer was started, then brokers, actually the whole cluster doesn't know that you already processed it, and on the next run, you will be delivered the same message. So we can do a double processing here. This may work for most scenarios. Actually, this is widely implemented because it's fast. You can achieve some idempotency on the consumer side by storing the offset ID in some database. Let's say you are dumping to database, so you can look into database, see if this message was actually processed. But yeah, it may work if you need at least once. Sometimes you may want at most once. For example, in telemetry, when you have sensors that send current temperature, if we lose some readings, this is not a problem. Probably the temperature didn't change for a while. How you do it in Kafka? Well, there is a fire and forget model. You set acknowledgements to 0, which means I fire notifications, but I don't need any acknowledgement, and brokers writes it or not. But there is a guarantee that there will be not any duplicates on this. The same for similarly for the consumer. You can imagine that you are consuming the data, but there is record you can't process because there is some issue with the record and your application is failing. So at least once scenario you would be still in this offset waiting for some operator to help. But if we move offset first and then process data, then even if this processing fails, then on the next run, after the restart, we'll just start including on offset 3. Okay? Still, this may be good for some telemetry data. But since the Kafka 0.11, they introduced the exactly once. And if you worked with distributed systems before, you may know that exactly once is not possible in distributed system. So they did something that we can call observably exactly once. So the messages can be duplicated, but we can't see the duplicates. On producer side, there is an extension to an API. Instead of message, we'll produce some sequence ID and then the producer ID. So even if acknowledgement is lost, when you try sending the message, broker will keep this in short cache that, this sequence ID was already provided. I already stored it. So this is a duplicate, you can continue working. This was easy, this idempotence. But what about consumers? Well, there is a trick. If your consumer reads the data from Kafka and puts them back to Kafka, so if you are in a closed system, you can use something that is implemented as transactional API. You remember, moving offsets is actually committing to other topic. So if you can do atomically 2 commits, like committing of our processing result and committing of the offsets move, we can achieve exactly once. But only in this scenario, if you are within Kafka. If you are connecting from Kafka to other system, there are a lot of dependencies. But still, if you are still within Kafka, there will be some unnecessary messages like uncommitted transactions, but the consumer can skip it. So you can do something like observably exactly once, which is great for business because a lot of use cases need this. They tested it. I mean the companies that are behind Kafka, Confluent, the most popular one. And this doesn't hurt the performance much. It just works. It's just 3% of degradation of the performance. I will skip this slide because it's not interesting. The security, who bothers? Yeah, there are some security capabilities, but I will focus on something that is maybe more interesting to you. The Kafka core may be not enough. I mean, the messaging is nice, but well, how to integrate the messaging in our system? First, if we talk using some kind of structure, you may want to know the structures. You may need the schema registry. So there is a component called schema registry that uses Kafka as a database backend. And if you produce data with some schema, let's say this is binary format like Avro, you can store the schema there, and consumer will be able to retrieve the schema and decode your binary messages. So this is something that really helps when you are evolving schemas. For example, when you are working with company that has a lot of microservices and you want some control over schemas. There is a Kafka Connect, the application that helps to connect Kafka to other systems. Like you can connect Kafka to database as a source, so you can get the data from database to Kafka, or as a sink, so from Kafka to any database. There is a large variety of connectors available, so you can try it out. Kafka Streams and KSQL. This is a framework for Kafka Streams is framework for in Kafka stream processing that simplifies things that are usually hard, like aggregation, windowing, joining. You can achieve them easily in a pretty nice functional language within Kafka Streams. And KSQL, really nice service that translates something like a la SQL syntax into Kafka Streams application. And it's also container for running this. So you can imagine accessing database console, then you access KSQL console, you type SQL, you hit enter, and this is Kafka Streams actually being developed, being run on some KSQL server. There is also a REST proxy for the languages that doesn't implement the Kafka protocol, so you can use it with curl, for example. If you are interested in more information about this, you can't miss tomorrow's session by Robin Moffat. He will do some demo session about how this all works together with Kafka. So I think this will be extremely interesting for you. There are, however, some weak points of Kafka. There is no support for retries on consumer side, on consuming side. So if you have a message that you can't process, you can't move the offset because the message will not be reprocessed. You can add some extra topics, you can add some buffers, but yeah, there is nothing out of the box. There is no message filtering capabilities. Let's say we have a temperature reading topic from all the data of the world, but we are interested only in reading here near the Hotel Galaxy. We still need to transfer all the data and filter this on the consumer side. Okay, Kafka will not provide us any subset of data. For consumers, we have only pull mode, so we can't easily. We don't have a push notifications. We can't be notified that some event was produced. There are some tools like Hermes from Allegro, the company I worked with for a long time, that does something like push model for consumers. There is even a Kafka Connect HTTP sync, so Kafka can read from topic and do HTTP requests. If you are writing a microservices system that communicate only via REST, this push is something that you may be interested in. You shouldn't share VM or any node on any machine that runs Kafka with other services, because it relies on this operating system caches. When you start Kafka, you can give it gigabyte of heap, and this will be enough for majority of use cases, and the rest of the memory on the RAM will be used for these caches. If you have more applications, they compete for resources, so you can have this cache contaminated, and your Kafka will be never fast enough. There is no UI in standard package. If you used Rabbit before or ActiveMQ, you know that after installing you have nice UI, you can configure things by the web. In Kafka there is nothing like this. There are some solutions, but they are not standard. And this is not the most lightweight protocol for IoT. This requires some knowledge and some, let's say there are better publish-subscribe systems like MQTT that really works well on systems that have kilobytes or megabytes of RAM. I'm already after the time, but let me just finish with the summary. I think that I feel like these easy foundations behind the Kafka, like let's just append the file, resulted in brilliant result. And I hope you feel the same, because the logic underneath is still the same. It will not change actually anywhere soon, because it just works. Kafka provides really high throughput due to these things. Kafka even, I read some article that Kafka works better on magnetic hard drives than on SSDs because it does this sequential write. And if you prepare a RAID arrays with 6 disks or something like this, you can achieve the better performance even than on SSD. It's perfectly scalable. If you need to double your capabilities, you double your hardware. There is no hidden catch here. You add the same set of brokers, and yeah, this works well. You may need some tuning, like increasing number of partitions, but yeah, it works well. It works well for every possible event-driven design. You know, there are designs like event notification, event carried state transfer, event sourcing, or CQRS. Kafka works perfectly well in all of these because it was designed to support all of these, and due to its simple nature, it just works well in all of them. If we want to start, if you like Docker, there is an image Wurstmeister Kafka Docker that simplifies installation. You just run Docker compose app and you have Kafka running together with Zookeeper. If you use Kubernetes, there is a Helm chart from Kafka called CP Helm charts that deploy Zookeeper, Kafka, and all open source stack deployed by Confluent. So you have Kafka Connect, KSQL, and so on. If you like the non-virtualized, you can systems or for example you want to feel the power on Kafka, you can download the jars and you can start JVM on your PC. I encourage you to try because you will be surprised about the performance of your laptops. I mean, yeah, when you run the web browser, yeah, this is running slow or something. Kafka will be really fast because it's designed to be fast. Thank you very much for listening, and I hope you have some questions. Yeah, please. Okay. The question was about durability guarantees to the Kafka. When you write something to Kafka and your broker, for example, dies before replicating the data, you would lose something. You can manage this by producer API. There are 3 options to tune the acknowledgements, actually. If you type 0, you get no acknowledge. If you type 1, you get durability on this one broker. So you will receive an acknowledgement after the message is persisted once. But if you type, I think, -1, then you will not get an acknowledge until the message is replicated to all replicas. So this is the way that you can decide in producer. This is not something strictly set from the brokers or from the cluster. This is maintained by producer. Any other questions? Please. Actually, I don't, but I did some experiments. If you use Kafka streams, which works in the closed system, like it reads from Kafka and writes to Kafka, exactly once is just a property. So you set exactly once to true, and it manages all for you. If you work outside, there is kind of code you need to implement, but yeah, I didn't ever implement. I played with Kafka streams, but when you test exactly once, it's hard to do this kind of failures, all kinds of failures you can expect, right? So yeah, it worked. I didn't lose any messages. I didn't receive duplicates, but I probably didn't do all kinds of failures I could expect. Yep. For example, if you want to have retries or dead letter queues or something like this, I used Rabbit once in the system that if I couldn't process a message, I just put this on the other topic that was designed to fire an event after a certain amount of time. So this was a delayed queue. So maybe in these scenarios, but there are options to mitigate it in Kafka, like creating a lot of partitions. So for example, you have 1,000 of partitions, and you have a problem with one message, you will still work in the 99.9 throughput, only this one will be blocked. So yeah, in this way you can mitigate this issue. Mm-hmm. Okay, the question is what about filtering? And usually if you want to provide some subsets, there is a way to do a filtering in form of Kafka Streams application. So for example, you have a users from Kraków, and you want that this second topic will be used heavily in your application. So you create a Kafka Streams application that does this filtering for you, and you join this second topic. Okay, there was one question. Yep, for Zookeeper, yeah. This is completely the same. You can with zero downtime. Oh, with zero downtime, you can really work with this with zero downtime. There is also one interesting thing I forgot to mention, because Kafka writes data in some log storage format. What if this log storage format changes? Like for Elasticsearch, it changes often. So Kafka provides the readers for all archival log storages. So every new segment will be rolled in the new version, but Kafka will still be able to read them all, the old ones. So even if you upgrade, there is no need to rewrite all data. It's all maintained by the cluster. Okay? The question is how many messages to keep. There are the segment is size limited, but you keep the messages using some kind of retention, and there are two options. You can do a retention by size, so you can say this topic cannot exceed 10 gigabytes, or by time. It depends on use case. You can use this one. Actually, the most of cases I know use this by time, because for example you set this to 24 hours, and you did adjust your alerting. So if something is not listening for more than half of this time, you want to do some pager duty alert to make people sure that the messages will be not lost.
So when some service goes down, you can actually change the segmenting time while the request is still working?
Yeah, exactly. If you know that the consumers will not keep up on reading, for example, this will be major downtime, you can increase the retention temporarily, so Kafka Log Cleaner will not remove the old data, and then you can shrink it. Yeah, it's dynamic. You set it in the. You just need to set it in the Zookeeper. Okay, you can still catch me later during the breaks. Thank you very much for listening.